Okay, everybody? Right. Okay, I'd like to welcome you all to this is the second session we have run today on training for the StarDrop Core and ADME QSAR modules that you have courtesy of BMGF. As most people are beginners, we're going to start right from the beginning, and Ed and Bailey are going to take you through how to visualize compounds and how to make your first forays into using StarDrop for looking at your own results. You should have access to the training files and receive the manual, and you can follow along or just sit and watch the presentation as you wish. I'll be recording the presentation so that you can review it afterwards and go back and revisit anything you didn't quite get first time around. So we find that's the most fruitful way of doing a training session like this. Okay, and without further ado, I think I'll turn you over to Ed. You can if you want to ask any questions, then please either unmute yourself and just ask at any point, or type something in the chat box and I'll ask it for you. Okay, over to you, Ed.
Brilliant. Thank you very much, Caroline. And yeah, welcome everybody to this training session. As Caroline said, myself and Bailey are going to be really giving you an introduction to StarDrop. And we're really going to do that largely through the use of some worked examples where we're demonstrating StarDrop, and hopefully you guys can play along at the same time, because I think it's easiest to learn about a bit of software when you actually try things for yourselves. And what I would encourage is, because you have myself and Bailey here at the end of the meeting, do feel free to interrupt us with questions as they come to you. I don't want this to seem too formal. I realize you can't look us in the eye and sort of wave your hands to us, but just jump in there, because it's the best opportunity you'll have to sort of be able to talk through things while we're with you already. So I'm sharing my screen at the moment. I have PowerPoint going, and I have just a couple of slides to show you to give you an introduction to what we're going to be doing. So I'm just sort of hopping into that presentation, and really I wanted to just sort of kick off by saying the objectives from our perspective today are to give you an introduction into how you can use StarDrop, and we're going to do this, as I said, through a combination of demonstrations and interactive examples. We are going to use slides occasionally through this session to give you an overview of the different concepts behind StarDrop, and some of the sort of science behind how we've done what we're doing and how we're using that as we're thinking about the decisions we're making with our compounds and their data. But one of the things I like to point out right at the very beginning is that there's a huge amount that you can do with StarDrop. We're not going to try and cover all of that, and so I like to point out a variety of sources of information that you have for helping you sort of learn more about StarDrop as you get into it and start using it with your own compounds and data. So just to take you through these very quickly, there is a user guide associated with StarDrop which really walks you through how you do things. And this is something you can get to from StarDrop itself, and I'll point that out to you very shortly. There is also a reference guide associated with StarDrop. And you think of this more like the scientific papers that back up the different analyses and approaches that we've taken within StarDrop. So it's more about the what does this mean kind of questions that you might have. And I tend to think of the reference guide as answering more of the interesting questions that you have about what's actually going on. But again, this is available from the StarDrop help menu. There are a number of online tutorials and hints and tips videos. Some of you may already have found these. If you have, you'll find out that they're very similar to the kind of thing we're going to do today. So the videos you can see or the tutorials you can download all walk you through with example data sets and take you through explaining how to do things in StarDrop and what the results mean. So you're very welcome to grab and try out any of those as you'd like to. And we can, of course, arrange follow-up sessions, whether that's for a group or just for a one-on-one. It doesn't have to be a long session like it's going to be today. It could just be for 5 minutes, hop into a TC with somebody from Optibrium, just to walk through something you're particularly struggling with or you've got questions about. So again, do feel free to ask. And in terms of asking, I've got highlighted in bold here at the very bottom. If there's one thing you take away from today, it's the fact that we have this lovely support address. For those of you that have already used it, you'll find that Bailey spends a lot of time looking after people who email this address, but you will always get any questions you send to this answered. And we're more than happy for you to use this for any questions that you have. Don't feel that because we've been through this session today, you don't want to ask a simple question about how do I create this visualization or how do I add a new compound to my data set. Please feel free to use it for anything at all that we might be able to help you with in terms of StarDrop. In terms of today's program, really what we've got is as a series of examples. They largely flow all the way through. We're going to work with similar compounds all the way through this set of different examples. But we're going to start off with an introductory session, sort of a getting started. We're going to get some compounds and data into StarDrop and create some visualizations and just look at ways you can use StarDrop to manipulate these and start looking for patterns. With then going to start moving on to what I think of as sort of slightly more advanced or more interesting things that you might want to do with your data, starting with approaches which are perhaps more in the hit to lead area, where we're going to be predicting some properties and looking at multi-parameter optimization. So thinking about how we can focus on compounds that have a good balance of properties. But we're then going to move on to some other examples that look more in the sort of lead optimization space. So we're going to do some SAR analysis, some interactive designing of compounds and using StarDrop's glowing molecule. Bailey and I are going to work together to take you through this. So I'm going to start off and give the sort of the first session, then Bailey's going to look after the next two, and then I'm going to come in just to wrap up at the very end. I should say the times on here are a little bit fluid. If this turns into a very interactive session, I don't want to discourage the questions or the tangents that we might take. Obviously, Bailey and I will try to make sure we get all the way through the material, but we're not going to be too hung up on whether one session is a bit longer than another. But this should give you a rough idea of what we are going to be covering today. And so really just as a one slide introduction to the sort of background behind StarDrop, really the whole principle behind StarDrop is focusing on those objectives that we all have in drug discovery, which are dealing with that multi-parameter optimization challenge that we all have. We're trying to identify chemistries which have an optimal balance of many properties. So please excuse it being cartoonified over here on the sort of right-hand side, but typically when we're looking for our hits or leads, we can find regions of chemistry space where we've got potency. And what we ultimately need to do as we start to optimize is move through that potency space to try and find a sweet spot where we retain that potency or improve it, but also manage to design compounds that have a good balance of all the other properties that we need in order to develop a successful drug. So safety, metabolic stability, absorption, solubility. There are many other properties that all need to be factored in at the same time. And of course, we need to quickly identify when we're in a situation where this kind of balance just isn't going to be possible. And again, I've rather cartoonified it down here in the bottom right. We may well find some potent compounds, but ultimately, if we can't get the balance of other properties that we need, we aren't going to come up with a successful drug. Now, the industry mantra for this is fail fast and fail cheap. But of course, we don't want to fail at all. And it's rather a negative thing on which to focus. What we really want to think about is the fact that we're working particularly early on in drug discovery with quite uncertain data. We work with sort of low quality or high throughput assays. We work with predictive models. And there's a lot of uncertainty in the data that we're using to make decisions. And of course, if we're going to make big decisions about taking projects forward or deciding to stop them, we need to understand the confidence we can have in our data in order to back up that decision. And so this confidence is going to be a sort of key theme you hear today as we think about how we use StarDrop to make decisions with the data we have available. And of course, the key to this, understanding the confidence in our data, is that we want to make sure we avoid missed opportunities. These are the potential casualties when we trust our data too much when it's potentially quite uncertain. So I promised that I wouldn't have lots of slides to get you going. This is just a sort of a placeholder introductory slide. What we're going to do now, I'm going to hop out of PowerPoint. And this is really the bit where you can all decide whether you'd like to join me in working along with StarDrop. I'd certainly encourage you to. So if you're in front of a computer and you have StarDrop with you, I'd very much encourage you to open it up and work along with me. What I'm going to be doing is working through the StarDrop training manual. I believe you all have copies of this. You don't need to look at that training manual now. I'm going to walk you through it slowly, and I'm going to do so at a pace that allows for the fact that if you're watching my screen to see what to do, you can't be doing something at the same time. So I will take things at a very steady pace, and I will try and judge that based upon any feedback that I get. What I would like to check is, firstly, is there anyone who'd like to be working along who hasn't quite got StarDrop set up yet, or doesn't quite know how to get it going? And alongside that, is there anyone who hasn't got the training files that we're going to be using? So this is a sort of what was a zipped up folder that contained these files here that I put on my screen. So some examples, some files that we will be using for the exercises that we do today. So just as a brief pause, if anyone has any questions about either running StarDrop or these files, now would be a brilliant time to shout.
Are we going to be using the auto modeler? Because I don't believe we have the license for that piece. But anyway, just wondering about that.
We're not going to cover the auto modeler today. I was going to sort of mention it very briefly at the end, but I believe there are going to be some follow-up sessions arranged, or certainly can be follow-up sessions arranged to look at some of the other modules of StarDrop. So the auto modeler is one of the optional parts of StarDrop, and we're going to focus today on the core functionality and the ADME QSAR module, which everybody has access to.
Oh, okay. Yeah. Thanks.
Yeah, Greg, we will run a second session, which will be just focused on the modules, and you're welcome to join us then.
Okay, thanks.
Okay, well, it's otherwise quiet, so I'm going to assume that you guys are either working along with me or you're happy watching. As I said, I'd encourage you to work along, if only because then you can try things out as we go, even if they're not the things that I specifically touch on myself, because you can use myself and Bailey to help you catch back up with us if you find you've done something strange to your compounds or data. But from this point onwards, I'm going to try and take things at an appropriate pace so that you can follow along and try things out for yourself. But do please shout out. I'm going to sort of assume that if I hear nothing, that everything's okay, but that always makes me a little nervous. So you'll find me checking in with you periodically. But do shout out if there's anything that you need clarified or you want me to repeat anything. So for those of you that got StarDrop open, hopefully you can all see something that looks a little bit like this. StarDrop's not very exciting when you first open it up and you haven't got any compounds or data to look at. But if anyone sees anything wildly different to my screen here, now's a great time to shout. Just by way of familiarization, I'm just going to point out some of the things we're going to be looking at. This big dark gray area here, we're very shortly going to fill up with a spreadsheet with some compounds and data in it. And over on the left-hand side here, we have a series of areas which you can get to through this variety of different sort of tabs at the top here. The first one you can see is visualization. As we go through the different sections today, you'll find that we use some of the different functionality in these different tabbed areas, which broadly split up the different areas or optional parts of StarDrop. At the very top, we have a menu, which is pretty standard in software, sort of for opening our files and getting to things. Some functionality for manipulating our data sets, whether that's finding things, tagging items, merging sets, sorting, and so on. Again, as I mentioned, I'm not going to try and touch on all of these things by any means, but it's useful that you have an idea of where to go looking for different functionality that might be useful to you. And the tools area has a number of analyses that you might like to apply to your data. And as I mentioned in the slide at the very beginning, we have a help menu. From the help menu, you have access to both the user guide and the reference guide, as well as a direct link to the community, where I mentioned that we have various tutorials, videos that you can look at. There's even a link you can click to sort of fire up an email to make direct contact with StarDrop support. So hopefully that sort of gives you a little bit of background as to sort of where a few things are within StarDrop. As we get going, you'll find that I quite often refer to this toolbar down the right-hand side. everything in the toolbar is available from the dataset or the tools menu somewhere, but often it provides a quick way to get to those different bits of functionality as we're working with our dataset. So I will try to refer to that if I particularly click on something there, but you can always get to those things from elsewhere. However, let's get things a little bit more interesting. So what we're going to do is open up one of the example files from our training data sets. And so I'm going to go to the File menu. And from the File menu, choose Open. And what you'll need to do then is browse to the folder where you've got those training files, because we're going to open up a particular SD file that we've saved in there. There's a few files with similar names, you'll notice. So I'll just leave this highlighted for a second, because the one we're going to open up is an SD file, which is called 5ht1a library.sdf. So once you've found that file, click the Open button. And you should see a dialog a little bit like this. So whenever you open up a text file, so a Smiles file, a CSV file from Excel, or a TXT file, or an SD file, as you're bringing the data into StarDrop, StarDrop is going to give you a preview of the data that it's going to present to you in a table. Now, when bringing data into StarDrop, StarDrop does its best to interpret the kind of data that you've got in any particular column within your data set. So you'll notice at the top of the preview window, StarDrop's got this little drop down at the top telling you that it thinks we've got some molecules in the first column, some text in the next column, some numbers, some categories. So it tries to work out the most likely type of data you have, because StarDrop can do different things with these different data types. If you've got really sparse data you're pulling in, sometimes StarDrop will simply treat properties as text. But if you happen to know they're a number instead, you can always click on this little drop down and change to whatever type you believe those data to be. So it provides a sort of a quick and easy way to preview what you're going to get when you open the data set up in StarDrop. And all we're going to do is simply click on the OK button. And that will open up this data set. And now we've got a spreadsheet visible in front of us. So this spreadsheet contains 285 compounds. There's a little message sort of down in the bottom right-hand corner telling you the number of rows and columns you've got in the data set. So obviously we can see there are simply 4 columns of data in here. We've got our compound structures. We've got an ID column. We've got a column which contains some measured affinities for our target, 5-HT1A. So these are as PKI values. And we've also got a category which indicates the series, the chemical series to which this belongs. Now, this series category is something that we've added to this data set, but we'll see later on how we can use StarDrop to group compounds together into series for you. So, but we're going to take advantage of the fact that we've got some of these categories in there just to help us out at the beginning here. So just as a very brief pause, I'm assuming that everyone is following along nicely with me, and everyone who wants to be following along is able to see everything I've got. But as I said, please shout out if that's not the case. Over on the left-hand side here, you'll see that we've got a histogram. So StarDrop has automatically plotted a histogram of our potency data because we haven't got very many properties in our table that we can add into a plot. We've really got this potency data and we've got these series. And so what StarDrop has automatically given us is a histogram which has plotted the number of compounds that we have in each of these series. And of course, this, while it's given this as a default visualization, we can create visualizations of whatever we like. So what we're going to do is change this into a different type of chart. So down in the bottom left here, we have a chart button. And if we click on that, we can see a list of different types of chart that we can create in StarDrop. And so I'm going to choose from this list the box plot. And because you need two properties for a box plot, we've got our series along the x-axis, and StarDrop has already sort of figured out that we're going to have our potencies on the y-axis. And what this is showing us is the distribution of potency values for each of the chemical series in this set. So for those of you not so familiar with box plots, they really allow you to see a distribution of property values. The line in the middle of the box shows the mean value. The box itself represents the 25th to 75th percentiles, and then the whiskers. These are actually configurable, but these show you up to the between the 10th and the 90th percentiles. Outside that, we then see any outliers. And of course, outliers often catch your eye, but really it's in terms of thinking about which series have the most potential, the box itself gives a much better feel for where sort of the mean and the sort of the bias of the potency values happen to lie. So what we're going to do, we've created this box plot. We can create as many charts as we like, and we can add them into dashboards. So obviously I've got this one visualization area here next to my data set. But if we click on this little button down at the bottom, there's a detach button, just sort of one in from the right. And if we click on this, it will pop a copy of our box plot into a dashboard window. We can make this dashboard window as big as we like, and we can also add further plots into this area. So our dashboard can gradually build up with as many charts as we'd like to see. One of the reasons we do this is that the chart visualization area itself responds as we interact with our data set. So if I select a column, you'll see it's now given me a histogram of the potencies because I selected the potency column. Charts in the dashboard aren't going to change unless you choose to change them. So popping charts into a dashboard really gives you the opportunity to keep the chart, but the chart itself is modifiable. Down the little bottom, there's a chevron that gives you access to all the same controls. You can change the chart types, you can change the properties on the axes once you've got some more properties in your data set. So popping a chart into a dashboard doesn't limit you in any way at all, but it allows you to keep the chart that you've created. What we're going to do, however, in our data set, I'm going to right click on this potency column. And you'll see that by right-clicking, I bring up a menu which is specific to that column, which enables me to sort these compounds in descending or ascending order. In this case, I'm going to choose descending to bring the most potent compounds to the top of the set. So this enables us to see very quickly that the most potent compound is from the indinol series. Its ID happens to be S534, which isn't a very exciting name, but it perhaps tallies with the fact that the indinols seem to have the highest distribution of potency values of all the different series we have available. But of course, as you'll have seen, we've got very little data in this data set to do too much visualization, so we're going to add a few more properties to this set, really to give us a chance to consider the relationship between potency and some of the simple drug-like properties of compounds in this library. So I'm going to change from the visualization tab and select the next tab along, which is the models tab. And we can see within here, under the section which is called StarDrop, we can see the ADME QSAR models, along with some, I guess, whole molecule properties, descriptors, you might say. What we're going to do to start with, we're going to come back and use some of the other models a little bit later on, but to start with, we're going to just focus on some simple properties. So we're going to select log P, molecular weight, donors, acceptors, TPSA, flexibility, and rotatable bonds. So by selecting this subset of the models, or the properties, these are the ones that we're going to add into our data set. In order to add them into the data set, all we need to do is click on this Go button at the bottom. You might notice as you become familiar with StarDrop, in quite a few places you'll see one of these blue arrows, which is the Do It button, the Go button. This is the button that does the thing which that part of StarDrop is all about. So in terms of the models area, clicking the Go button is what's going to run the models. So if I click this, run those models, and for a few properties, for a small number of compounds. As I said, we've only got 285 compounds here. It only takes a matter of seconds to add these calculations into our data set. What you'll see is that we now have a column added for each of those properties. And so our spreadsheet is just a little bit more interesting now to work with. We're going to use this to create a slightly more interesting visualization. So I'm going to swap back to the visualization area. And I'm going to go back to the chart button at the bottom. And this time I'm going to select 2D scatter. Now for this scatter, what I'm going to do, I want to have my potency on the x-axis and my log p on the y-axis. It happened to give me those, but if I wanted to change the properties on axes, simply clicking the drop-down enables me to choose any other property. And if you've got a really big data set, typing into the search box at the top, as you type, it will hide things from the list to help it make it easy to find things. As I mentioned, I want to have log p on this y-axis and potency on the x-axis, so I'm going to leave it as it is. What I'm going to do is pop this into my dashboard. So again, I'm going to click the detach button. And I'm going to make my dashboard a little bit wider so that I can see my box plot alongside my scatter plot. And in the bottom right of my scatter plot window, I'm going to click on this little chevron just to show me all the different controls. And so that enables me to then start formatting this chart. So there is a little color button just to the right here. So this is the format chart button. If I click this, it will open up a window that enables me to configure how I'd like to format the points which is showing in this chart. So what I'm going to do is change the color of the points so that they're colored on the basis of the topological polar surface area. I'm then going to size the points based upon the number of hydrogen bond donors. And I'm going to set symbols based upon the number of rotatable bonds. So as you see, we can start adding dimensions to this chart using symbols, size, colors. We also have borders and transparencies that we could use to again, modify this chart further and add more properties in. But as you see, as we change these, the chart itself updates to show us what we've chosen. And we also see a key which gives us an idea of how we've set up the formatting for this particular chart. So again, just to check in, as I've changed a few things here. I'm assuming everyone is with me, but I'm going to give you a few seconds just to shout if anyone has got something different going on and would like some assistance. Okay, I'll take the silence as everyone being perfectly happy. That's brilliant. I'm going to close this formatting dialog. I'm going to make my dashboard just slightly bigger because what we're going to do is think about what we've done with this chart. We're actually going to apply some filters to this as well to remove some compounds or remove some points from this chart. So I can get to the filters by clicking on the little hamburger menu and choosing filter. Now I haven't got any filters at the moment. I've got this empty filter window, but if I click the add button, I can choose from a list of the properties. And so I can filter on the basis of molecular weight, if I choose MW from the list. And when I do so, you'll see it gives me a little range that I can use for filtering. Now I can drag this to remove points, and you see they disappear as I do so. Change the bottom end of the range. I can even click on this to invert the range. So if I want to sort of create a region and sort of exclude in the middle of that, I can invert the range too. But what I really want is to simply filter out all those compounds with a molecular weight greater than 300. So in this case, I'm going to type that into this upper box here. so that it leaves me only with points which have a molecular weight less than 300. So, what we can see if I move this filter out of the way as well, I do have the option to apply the filter to all my charts at the same time. So if I tick this box, we'll see not only is the scatter plot being filtered, but my box plot has been filtered as well. And we can see that with this particular criteria on the molecular weight, I'm only left with aminotetralenes and aporphines in terms of my chemical series. Now, what I'm going to do is clear my filters, so I'm not hiding any of the data. So click the clear button, and close this dialog. And then I'm going to minimize this dashboard for the time being. So I'm going to just move it out of the way so that I'm not going to close it to lose it, but I'm going to just move it out of the way by minimizing it. And we've currently been looking at this data set in terms of a spreadsheet. I'm sure you're all familiar with working with spreadsheets, but we have a number of different ways in StarDrop that we can look at our compounds and their associated data. And so one of the other views we can use, other than this table view, is something that we call card view. So over on the right-hand side on the toolbar, up near the top three buttons will enable you to change between different views of the compounds and their data. And you can swap back and forth anytime you like, and it'll preserve what you were previously looking at. But we're going to switch into card view by clicking the third button down. And what we now see is every row that was in our table previously is now represented by a single card. Now the cards themselves, you can see show the compounds and some of the original properties that we had in the data set, the IDs, the potencies, and the chemical series. But we can change the design to show whatever we'd like. So we can design cards to show whatever properties are of interest to us. So what I'm going to do is from the design menu, click all properties. I apologize, my design menu popped up. It was hidden, I think, by I don't know if that was by the meeting, but if you click design menu, you should see all properties there. Once you click on that, all the properties will be added to the cards. So we can use this view of all the properties in order to start making comparisons between compounds in a slightly more sort of focused way. The first thing to point out is that although we can see our compounds arranged as cards, they're laid out on a desktop that is movable and sort of infinitely expandable. So if you move the icon, the cursor, which will appear as a hand somewhere on the empty desktop, click the mouse, click and drag, you'll find you can move it around. So if I drag it down a little bit and make a little bit of space at the top, I can then move cards around on the desktop to wherever I like. So I can grab this second card, move it up here, third card, move it alongside it, fourth card. So if I wanted to focus on these three compounds, I should say that the cards have been ordered in the same way we had them in the data set. So the most potent compounds are here in the top left. So although I haven't taken the most potent compound, the three I've taken are still very potent compounds here. And what I can do is zoom in and focus on the properties of those cards. So I'm using the mouse wheel to zoom in, but you can also use the control plus and minus keys to zoom in and out if you don't have a mouse wheel. What I should also point out is that although we added all the properties to the cards, we can't see all the properties on this particular card design. The cards themselves have multiple pages, and I can switch between the pages of the card in order to sort of compare different properties. So if I do design a card which has particular properties on different pages, it's very easy to switch between them, and all cards always show the same page at the same time. So what we're going to do is have a little look at the distribution of the log p values across all the different cards, so the cards that represent the compounds in the data set. So I'm going to zoom back out again, and I'm going to reset my view a little bit. So now at any point, if you've moved cards around, you can very quickly tidy up the view by clicking on the layout and then the grid button. And that will tidy your cards up into a grid again. Again, if I zoom in and I want to change page, I can do so. So it doesn't matter really what zoom level I'm at. Whenever I choose to lay out in a grid, it will create me a grid which fits the width of the screen I've got at the zoom level I'm currently working. So, and you'll see this somewhat mirrored in the little sort of mini map down in the bottom right here, which gives you an idea of where you are looking at in terms of all the cards that you've got available. Just like visualizations, we can use formatting on our cards. And so I'm going to click the format button to open up the format dialog. And I can use this now to color my cards on the basis of log P. Now, give me a default color range of red to yellow, and it's going from the lowest log P in the data set to the highest log P. We can change this around using these drop downs to choose any colors we like. So your artistic skills can come to the fore. What I'm going to do, just to be consistent with what we'll be doing elsewhere in StarDrop, where we're going to use yellow for the best values and red for the worst ones, I'm going to swap this round so that the highest log P values are red and the lowest log P values are yellow. But as I said, there are many different formatting options for you to choose how to color your compounds and your cards. I'm going to apply this by clicking OK. And now my cards are colored. So as the lowest log P cards are yellow, highest are red, but they're ordered in terms of the potency. So we can see at the top of this data set, there's sort of fairly red, fairly orangey cards up here. There's some slightly sort of lighter orange ones within there, but we get a feel for the fact that there is a sort of a spread of log P values across these most potent compounds. So up to this point, we've been really considering compounds individually. But of course, at this stage in a project, we're sort of early on, we're really thinking about the results of some hit finding. It's quite common to look for series of compounds with good properties so that we can focus on those particular series. Now, of course, I mentioned at the beginning that we've added a flag or a category to our data set telling us about series. But as I mentioned, we can use StarDrop to start grouping series of compounds together automatically, even if you don't have that as part of your data set. So what we're going to do is use a clustering approach while we're looking at card view. So from card view's analyze menu, going to choose clustering, and we have three different ways that we can cluster our compounds. We can either cluster on the basis of common substructures, or on the whole structure, or on the basis of properties in the data set. Now, in this case, we're going to do it on the basis of common substructures. So I'm simply going to click the cluster button. What this is going to do is cluster the cards together so that those that share a common substructure get stacked on top of each other. So we've got the concept of cards, and now these cards have automatically been stacked together. I'm going to focus in, just zoom in slightly here. And as I said, we can sort of move the desktop around as we want to. So as you want to focus in on different regions of it, simply hover the mouse over that and zoom in. For any of these stacks here, we can right click and choose inspect. And that enables us to see the cards that lie within that stack. So indeed, if you looked within a stack and decided, I don't want this card here, we could pick it up, move that back onto the desktop. Or if we want to put it back in the stack, just move it over the stack, drop it in. So stacks can be created manually by dropping cards on top of each other, but they can also be created using these different analysis processes. But by inspecting a stack, by right-clicking and choosing inspect, or simply double-clicking, we can always see the cards that we've got within. Now, the reason we might want to do this, and the reason we want to sort of inspect the results of the clustering we've applied, is because really any clustering approach introduces artificial boundaries between different groups based upon the different whatever algorithm you've used for your clustering. So being able to apply a chemist's eye and refine the stacks is often an important part of making sure that you have appropriate compounds clustered together. So what you'll probably notice if we zoom in here, we've got these different amino tetralenes here which have been put into different clusters, but we can see they all still share the same sort of ring-based common substructure, the 3 fused rings, and we can easily refine this stack simply by grabbing one stack, dropping it on top of another. And what you'll see is that the common substructure is updated to reflect the fact we've now combined these. What we can also do as we continue to refine these stacks is refine the view we've got of them. So the clustering approach automatically showed us a count at the very top of the number of compounds across the data set, and also the substructure in that stack. But what we're going to do is change the design a little bit, and we can do that by choosing the design menu. And choosing custom, and that will bring up the card view design preferences dialog. So a dialog a little bit like this. And what we're going to do is change our stack design here. So within the design area itself, we can see different items that are laid out on the stack, and we can click them and drag them off. So I can clear my stack design. Over on the left-hand side, we can see different things we might add to a stack design. So under the general section, I could add a representative structure. But then I can, under my histograms, I can grab the 5-HT1A affinity and drop that in. And again, you can see I get choices where that's going to be laid out relative to other items on my design. I can also add little box plots. So I might add a little box plot of log P as well. I'm going to put that at the very bottom. You can change the size of the cards and the stacks again by resizing as you wish. So if you want wider cards with more properties in columns, or taller ones with more properties, there's a lot of freedom there. But the key thing is that you understand you can sort of design cards and stacks to show whatever you'd like to see. So having designed my new stack, click OK. So I can now see these properties laid out on the stacks I have available. As I mentioned, we can use this approach to refine the series in our data set. And if you do stack cards together, from the Organize menu, you can choose Stack and then save stack details to the data set. And that will enable you to create a column which stores a classifier of how you've stacked your compounds together, your cards together. So you can always get back to them if you like. But of course, this data set already has the series column where we've got our different categories, different series in the data set. So what I'm going to do from the Organize menu is choose Stack and then by property to enable me to choose the property I'd like to stack the cards together by. So in this case, I'm going to choose Series from the menu and then click OK. Now, if I zoom out very slightly, we can then see one stack representing each of the 6 different chemical series in this set. So if I move that up to the very top here and then open my dashboard again, you can sort of see these laid out next to each other. So I have these different representations. And of course, we have a box plot which already represents sort of one box per series. But now we could sort of very quickly start to get a picture of what might happen if we were to perhaps focus on compounds in the bottom right of this visualization. So if we were looking for the most potent low log P compounds, and I were to select some of these, we could quickly see which of the different series they belong to. Whilst it's highlighted in the visualizations, seeing it on the stacks gives you an idea of the proportion of that stack which is included in the selection that we've now made. Now, of course, we've started to create some visualizations, we've interacted with our compounds, and at any point, if you want to save what you're working on so that you can come back to it or share your desktop, as your StarDrop desktop, with anyone else, from the file menu, simply choosing Save Project will save all the visualizations you've got, your data sets, whether you've got opened one or more data sets at a time, and enable you to start again from where you were and share that with other people. So I won't save this, but if you've been particularly creative during the session and would like to save what you've done, by all means, save this and just to try this out. So that was everything I intended to cover as a quick introduction to some of the sort of visualizations and simple things we can do with compounds and their properties in StarDrop. The next sections are going to move on to looking at doing a little bit more rigorous multi-parameter optimization. But before we move on, are there any questions with what we've covered so far?
Ed, one of the most useful things I find is the ability to take the pictures out into something like PowerPoint. Would you like to just demonstrate that?
Yes, certainly. So there's actually a variety of things we can do for getting things out into PowerPoint that you're alluding to there, Caroline. So just by way of different examples of things you might do. So any visualization you've got going, if you right click on that, you'll notice there is an image option which we can copy or save. So choosing copy would put it onto my desktop so I can drop that straight into a presentation. You'll find if you right click on the card view desktop, you can do exactly the same. So if I happen to have a sort of particular view of cards laid out and thought, no, I just want to grab that, again, right click, copy image, so I can take this and drop this into a presentation. What we can also do is copy an image of an individual stack. So again, right click, copy image. There's a pattern here. There's a lot of places in StarDrop where right clicking will enable you to copy an image out. And I'm not sure if Caroline, you were referring also to the exporting to PowerPoint options. So we also have options for, under the dataset menu, we can export out selections of compounds and their properties and directly create PowerPoint slides. If that was, is that the kind of thing you had in mind there, Caroline? Because I'd be very happy to demonstrate that too, if you think that would be good.
Yes, I think there's a really useful thing, because once you've got your beautiful analysis all set up and you really want to share it with people who haven't got StarDrop on their desktops, it's a really nice feature.
Yes. So the direct export to PowerPoint, obviously all the others give you a copy and you can paste directly into PowerPoint. But if perhaps you wanted to create a snapshot of a few compounds and their properties, so let's say I want that first compound and then 3 or 4 others, excuse me. So I'm selecting a row and I'm holding down Control and then selecting, so I've selected 5 different rows there. And it could be that I'm interested in the ID, the structure, the potency, the log P. So what I'm really doing by selecting rows and columns is creating a subset of these so that I can create myself a small like SAR-like table in PowerPoint. So if I select those and then choose Dataset Export to PowerPoint, I should say this is a feature that works on Windows as opposed to Mac. So I apologize to Mac users. We haven't yet got this going on Mac. But in PowerPoint, if I just sort of trot back to that, you'll see that it's created me a slide automatically. So it's created a table. It's effectively pivoted the data to put structures at the top and then those properties below that I had selected. So as a way of getting sort of a bunch of properties in and out of PowerPoint is a very quick way to do that. And these are all editable, so this is just written in as text. The structures are in as images. So the structures are harder to manipulate because they're images sort of pasted into that table directly. But hopefully this provides a really quick way to get some sort of compounds and their properties sort of out of StarDrop into a presentation.
Actually, I think I did find that you could take the data out into Word, but not into PowerPoint.
Okay, yes. So you can, of course, got you. Yeah, this direct export to PowerPoint is definitely Windows only. But if I were to simply click, right-click and choose Copy, that would also copy these out effectively as text and HTML. So I can paste them into Word and PowerPoint. It's not as neat as the direct PowerPoint export, but it does enable you to get these out if you'd like them. So you can always get anything from StarDrop out for other applications.
I think anything that saves you having to redraw structures and remake data slides is a good thing.
Oh, absolutely, yes.
Any other questions? Nope. In which case, shall we move on to the next section?
Yeah, in which case, what I'm going to do, as I mentioned, I'm going to hand over to my colleague Bailey, who's going to introduce the next section. So I think, Caroline, you'll need to swap over controls of who's got control. And then, yeah, I shall leave you in Bailey's hands for the next couple of sections.
I think what you need to do is you need to stop sharing and Bailey needs to start sharing.
Okay. There we go. So I've stopped sharing. It's all yours, Bailey.
Yes, okay.
Perfect.
Right, can you see my screen?
Yes.
Okay. Right, so this next section is, and then we're going to go into some multi-parameter optimization and have a look at some other properties. Right, so in the previous example, we used simple drug-like properties along with potency.
Bailey, you've gone into presenter. You've gone into presenter view, and I can see the presenter view. Can you just go into slide view?
Is that going to go? Oh, yeah, sorry.
No, it's going into.
Sorry, I've just got a new laptop and it's going to work. Nice things.
Well, just zoom in a bit.
Yeah. Sorry about this. User slideshow. Will that work? Yes. Okay.
Yes. Perfect.
Right. Okay. Right, so in the previous example, we had a look at some very basic drug-like properties along with potency in order to prioritize the compounds. However, in practice, we deal with much more complex data. And one method that chemists typically use in order to prioritize compounds is filtering. So in this illustration, we're using an analogy of finding a diamond amongst coal. And this represents finding your best compound amongst all of the other compounds. So we typically define a set of filters, and we define some cutoffs, and any drugs that don't meet that required property are thrown out. And we hope in the end, out of this process, we get the diamond. However, in practice, this is often not the case, and this is due to an accumulation of error during these stages. So by the time you get to the end, there's actually a very high likelihood that you won't get the best compound out. It's often the case that the best compound might be thrown out, due to a harsh filter, or you might be left with an awful situation where you get a drug out the end, but this is not the best drug. And that could lead to things like a late stage failure and very costly mistake. So the reason for that was the uncertainty in the data, but what is the source of this uncertainty? So we know that when we're working with experimental data, there is always an error associated with that data. No assay is perfect, and that's why we do an assay many times. Sorry, and we get multiple data points for every assay. And we also look at the standard deviation and standard error and make sure that we can be confident of this data. So that's the experimental variability, but there is also uncertainty associated with predictions. And this can be assessed through validation of the models. So with the predictions done in StarDrop, I'll show you how where we can find this uncertainty value. When we're working with predictions, we also need to think about the domain of applicability of the model. And this is the chemical space to which we can apply that model. So if a model is very general, if it has taken into account a wide range of compounds, then we can perhaps be more confident in throwing it at any compound, whereas local models have a smaller domain of applicability to which they can be applied. So our unique approach to multi-parameter optimization is through the creation of a probabilistic scoring profile. And this is a method of ranking compounds based on their likelihood of success using all of the available data, and it also takes into account the uncertainty in each predicted or experimental point. And that allows for the user to be able to make a decision with confidence about whether two compounds can be distinguished with confidence. On the left here, we have an example of a user's scoring profile. So you've got all the properties that matter to you, and then you enter in desired values. These can be a hard cutoff or a range of properties that are desirable for that property. And then you also assign an importance. So this is telling StarDrop how important that property is. So for things like affinity, that's a very important property, so that we would set the importance very high for that. So what you get out of the scoring profile is this histogram shown here, as well as the score. And this histogram provides a very quick visualization showing why that compound got that score. The height of the bars correspond to how well that compound did for that property. So a high bar shows that the value is within the desirable range, and it also shows that we are confident that that value is within that desirable range. Whereas the lower bars indicate that we're either the compound is either not within that desirable range, or that the error spans that range or goes outside that range, so we're not confident that it is actually within that desirable range. Right, so I said that the output of the scoring profile is a histogram, but you also get a score out. And that's a number between 0 and 1, indicating the likelihood of success based on that scoring profile criteria. And you can use what we term a snake plot in order to assess all of the compounds within your data set. So this is a snake plot down here. We've got our the compounds shown going from best to worst in terms of their score. And we have whiskers on this plot showing the confidence interval for each of the scores that indicates the uncertainty in that score. So in this case, we can see that we can't really distinguish between the top 5 compounds. They're all very similar in terms of score, and they have quite big whiskers. But we can say with confidence that the bottom 50% can be rejected with confidence because these whiskers don't reach near to the bottom of the ones with higher scores. So we can say with confidence that those are worse drugs. Okay, so I'll just go back into StarDrop now, and we'll have a look at some of this in practice. Right, so if everybody goes back into StarDrop, we're going to be working with the same data set. And we're going to be have a look at some more properties and see how we can apply these scoring profiles to these compounds and look at a wider range of ADME and physicochemical properties. And we're also going to have a look at the uncertainty and the statistical error so that we can make sure that we're not getting rid of any compounds that might have promise, and so that we're making sure that we don't miss any valuable opportunities. Right, so we'll just go into the table view. So if you click on the top icon on the right-hand toolbar, so back into table view, and so the data that we imported into StarDrop did not have any uncertainty associated with it. So we'll just edit that so that it does. If we right-click on the column header, we'll go down to this Edit button. And within this window, we can specify the type of data that is in that column and also give it a default uncertainty value. So here we can say that this is a concentration, and it is a pKi value, so it's automatically chosen pKi. And then we're going to select this use default value for all data. And I'm going to set this to 0.3, and that corresponds to a twofold variation in Ki values. But this is pKi, so it's log data, 0.3. And then we'll select OK. And if I select this button on the right, this normal distribution curve with the percentage sign on it, then that shows me the error associated with that. And we can also have a look at the error associated with our predictions. So, for example, we can see the error for the log P prediction. And we can switch that off by just clicking on that icon again. Okay. So now we're going to have a look at some more properties. So if we switch over to the Models tab, this second tab on the left, and we're going to calculate all of the available models in StarDrop. So if you just click on that StarDrop box, it'll select them all. And then we'll click on this Go button to tell StarDrop to go away and calculate or predict all of these properties. So it's a bit of a race to see whose laptop is fastest and who finishes first. Okay. And there we go, we've got all of that data now on the end. And now what we're going to do is we're going to create a simple scoring profile and apply that to these compounds. So if we go over to the scoring tab, and we're going to select one of these scoring profiles shown in this window here. So these are just some general scoring profiles that you can use. So if I click on Oral CNS Scoring Profile, you'll see that that then pops up a scoring profile in this top window. We'll use this Oral CNS because we would like to ideally get an orally dosed drug that can pass through the blood-brain barrier, because these are 5-HT1A agonists. So from here, so this scoring profile takes into account lots of properties. However, it's not taking into account that experimental data of that PKI data. So we're going to add that in. So I'll just, within this second box, I'm going to have a look for that PKI data, and it will probably be at the bottom. So I can see that data's there. And I'm just going to select that and then drag that to the top, and that adds it to the scoring profile. I'm then going to set a cutoff for this. So I'd say I would like these values to be greater than 7. And I'd like my importance to be very high. This is a very important property. However, in practice, the cutoff of a PKI of 7 is not very practical. We might have a compound that has a PKI of 6.9, but it has very good properties. So we don't necessarily want to just use a hard cutoff at this stage, because those drugs might be quite interesting, or the drugs that are close to 7. So we really want more of a gray area rather than a hard black and white cutoff. So what I'm going to do is I'm going to create a slope from 8 to 7. So in order to create a soft cutoff, you can either select the property and go to Edit, or you can double click on the property. And this brings up a score editor. So within here, you can insert a range, and that allows you to create a slope. So I'll set my minimum value to 7, my maximum value to 8. I'll give compounds with a PKI of 7 a score of 0.05, and set the score to 1 for compounds of 8 and higher. So once I've got that set, I can click OK. And there we see that we've got a nice slope. And I'll just change this value to 0.05. There we see that compounds that have a lower PKI are penalized quite heavily. That's shown by the red color, and the green color indicates that these compounds score highly for this property. So we can click OK, and we see that we have this symbol here, which indicates that this is a more complex range than just a hard cutoff. And we can give our scoring profile a name. So I'll call this one Potent Plus Oral CNS Scoring Profile. We can also save these scoring profiles. So if I wanted to save this scoring profile to the project so that it's available whenever I open this project, I can click Save to Project, and it's now available within these scoring profiles shown here. I can also save it to a file, and that means that I can perhaps share it with other people, maybe other members of the team, maybe to make sure that everybody's on the same page, everybody's working towards the same goals. So that can be quite handy. So what we're going to do now is we're going to run the scoring profile on this set of compounds, and we do that by clicking on this Go button. click that button, and it's calculated all the scores. We can now have a look at one of these snake plots that I described in the slides. So if we pop over to the visualization tab, we can either select snake plot from this chart, or you can also just click on this column header and it will create a snake plot. So we can see that we've got all of our compounds going from best compounds, best scoring compounds to lowest. So I can go back to card view and have a look at which compounds are scoring highest, which from these series are scoring the highest. So as Ed showed, these plots are very interactive. If I lasso around some compounds, say the first 100, so I'm just holding down the left mouse key and drawing around some of these data points, I can see that most of these compounds are from 4 of these series, as we've shown in the last example. So these seem to be the most promising series, whereas these 2 series seem to not be as promising and perhaps not worth taking through the drug discovery process. Right, so just stop there for a second and ask whether there are any questions at this stage. Just check the chat or anything. Okay. So I'll go on to this next section. So in this next section, we're going to have a look at how StarDrop can help with looking at structure-activity relationships, and also seeing how we can use StarDrop to redesign compounds in order to optimize their properties. So we'll just close this project and open up a different data set. So if you want to save this project, you can do that, go to File and Save Project, but we'll just go to, otherwise just go to Close Project and discard that. So the next data set we're going to open is this aryl pyrazine series S10. And that's a StarDrop data set file. So I'll just give you a second to find that file. So this compound is the aryl pyrazine series from the previous example. So this data set contains drugs that are, it contains this buspirone drug as well as some very similar compounds. Now, buspirone has a problem in that it has a very short half-life. So it was marketed as an anti-anxiety drug. So we're going to be using this as an example data set. Right, so we'll switch over to card view. So if you switch to this third icon, go to the third icon on the right, and then we're going to find a particular drug, and we can do that using this magnifying glass icon here. And we'll just go find a compound called S10-14. So if we type that into the text field and then click Find Next, it will highlight that compound in the dataset. And there we go, it's found it. Next, what we're going to do is have a look at an activity neighborhood analysis. So this analysis is useful for identifying activity cliffs, and that's where a small change in the structure of a compound leads to a large change in the activity. So it indicates good SAR changes. So you've got that compound selected, and then we're going to go to Analyze and Activity Neighborhood. So we're going to leave these settings as default, but I'll just mention that you can change the number of nearest neighbors, and you'll see that as you change the number of nearest neighbors, the similarity threshold changes as well. And we're going to be coloring the links by the difference in 5HD1A affinity. So we click OK, and now we see a spiral pattern of all the cards. So there is a lot of other information that you get out from this analysis, but I won't go into that today, so I'll just minimize that for now. Okay, so let's have a look at these cards. So one thing that I mentioned that was very important for this particular project is the half-life. So we're going to color the cards by this property. So if you go to this Format Chart Type button up here, we can then choose to color by this CYP3A4 half-life. And this has a range from 2.9 to 78. However, this is a bit high, so I'll just change that to 40 minutes, and then click OK. And we can see that the cards are now colored. So let's have a look at these. So we've got the nearest neighbor compound, so the most similar to the query molecule shown on the right of the compound, to the right. And then the cards are getting more dissimilar as they spiral outwards. So if we hover over these links, we can see the two cards. So we can see that in this case, there's a change with the left side of the compound. So you can see that one compound has a paramethoxy, keep sneezing, paramethoxy group on the benzyl ring. And we can see that the arrow is pointing towards the query compound, indicating that this methoxy group is actually decreasing its potency. If we look at these two compounds, we see that the arrow is pointing towards this compound, and this compound has an ortho methoxy group. So it's quite interesting that the paramethoxy group causes a decrease in the potency, whereas the orthomethoxy group actually increases potency. So the positioning of that is very important. And we can zoom out a bit more, have a look at these compounds. So we're also interested in the half-life. And you can see that there is a very bright yellow colored card at the top. And have a look at that card. So this one's a bit more dissimilar to the query compound, and we can see that it's different on the left-hand side as well as the right-hand side. So both sides of the compound have been altered. We can see that it has this desirable change on the left-hand side. We've got this orthomethoxy group, and on the right-hand side, it's been changed from a spiro group to a dimethyl group. So that's quite interesting. We can say that we can attribute the half-life to the right-hand side of the compound, because we know that changing just the left-hand side, adding that orthomethoxy group, doesn't lead to an increase in half-life, but it does lead to an increase in affinity. So you can see some interesting patterns emerging. Another way that we can have a look at the relationship between various groups and their properties is through an R group decomposition. So we'll just switch over to the table view and have a look at an R group decomposition. So we select this top icon on the top, sorry, on the right-hand toolbar, and then if we go to click on this R1 button, it's the last tool on the right. You can see that a window pops up saying select scaffold. So the regions that we're interested in their changes are this left-hand side of the molecule and the right-hand side of the molecule. And we're also interested in any differences within this linker region. So what we're going to do is we're going to select two regions to be our scaffold. So I'm going to select this piperazine. I'll just draw around that, holding down my left mouse key, and then I'll press Control in order to select the piperidine dione as well. I'll just draw around that, holding down Control. There we go. If I click Next, you can see that it's labeled the R groups in the variable linker. I can also change these, so I can add another R group if I wanted, or I could change atoms into any atom. So if that was an N for some of these compounds, but it was a C for other compounds, I could change that to an X, and that would allow for that variation within that scaffold. Okay, but I'll just leave it as default, so I'll just select back and then next to reverse those changes that I've made. And then if I click next, you can give this analysis a name. I'll just leave it as analysis 1. And then you can click finish. And now you can see that it's gone away and created a table of the various L1, these are the linker regions, and the R groups, all of these compounds. So as we showed these, when you click on a column, it creates a histogram, and the same is true for the R groups. So if we click on two columns, then we can see that an SAR column, that an SAR plot is created. Now it's just holding down the Control key before clicking on the second column. So here I have an SAR plot of the linker region versus the group at the R1 position. And the size of the dots is corresponding to the number of compounds that have that combination of R3 and linker. But we can change that. So similarly to our other plots, we can also color or size or change these data points based on other properties. So let's have a go at doing that. So we said that that affinity is very important. So let's color these data points by affinity. So I'll just select 5HT1A affinity. And another thing we said was important is the half-life. So I'll size the data points rather than by count. I'll size them by the half-life. It's 304 T half. Right, so close that. And so now I'm looking for data points that are large, but that also are very yellow, indicating that they're quite potent. And when there's more than one compound for this combination, then it takes an average of those properties. So we can see that, I'll just reset that. We can see that this group with the orthomethoxy group, which we identified earlier, is also coming up in this SAR plot as an interesting R group that is got good properties. We can also see some compounds that or some substitutions that are not very beneficial, so that have small red data points. Okay, so at this point, I'll just ask if there are any questions. Otherwise, I'll just pop back into the slides. Right, so are there any questions? Okie dokie. Right, so I'll just introduce the design tab of StarDrop. So within this tool, the compounds are shown as a glowing molecule, indicating the regions or the groups on the molecule which contribute to an increase or a decrease in a particular property. So this allows the user to see the regions of the molecule which might need changing in order to optimize that property, and it also shows why that compound received that particular score. So red means that the property is increasing. I mean, that region contributes towards an increase in that value for the property, and blue means that it's causing a decrease for that property. So depending on the property, the red regions can be good or bad. For example, if it was solubility, then you would like to see more red regions and less blue regions. It's generally like to have quite soluble drugs. Whereas for something like hERG inhibition, you'd like to see more blue regions. You'd like to see a lower inhibition of hERG. And these glowing molecules, the glowing molecule can be applied to all of the StarDrop models, and it can also be applied to these scores. So you can have a look at you can take kind of a holistic view of the score, see which regions contribute towards that or decrease that. And then you can also use the glowing molecule on auto modeler modules. So any models that are built with that, you can use this tool. Okay, so that was just a quick deviation into the slides. And now I'll go back into StarDrop. Right, so in this data set, we have experimental data. So you have the pKi as well as the CYP3A4 half-life. However, now we're going to have a look at designing some new compounds. And we are going to load in a model of the pKi in order to be able to determine these values for any new compounds, or predict this value for any new compounds. So we're going to go over to the Models tab and open up this pKi model. So you go to the Models tab and then click on this folder, and then navigate to your training files, and we're going to open up this aralpivarisin local model.aim file. So if you could find that file and then click open, and we can see that that's now available under the custom tab. We'd also like to assess how good any new compounds are in terms of their overall balance of properties as well. So we're going to also open up a scoring profile. So let's go over to the scoring tab, and if we go to open, click on this folder button again, and again navigate to your training files, and we're going to open up this potent plus oral CNS scoring profile. Click open, see that that's now in this scoring profile window. And now we're going to run this scoring profile on our data, on our compounds. So we click this Go button, that goes away and calculates the scores. And we're going to have a look at one of our favorite molecules, this S10-14 compound. So if we go back to this magnifying glass to find this compound, so I've already got the text in there. I can just click Find Next, and it'll go away and find the compound. So there, it's highlighted that compound. Right. So now I'm going to switch to our third viewer mode, which is called Molecule View, and it's the second button down on the right-hand toolbar. So if we click there, we can see this selected compound here, and this is quite a good viewer for having a look at all these properties together. So instead of having a table view where you can see a few properties for all of the compounds, you can have a look at quite a few more properties for just one compound. And then we're going to switch to the Design tab. If you click on this Design tab here, you can see that this compound is shown within the designer. I'll just introduce quickly the designer. We have, because it is quite different to some other tools. So you can use this line drawer to draw single bonds. You can hover over that bond to create, and then click to create a double bond, and then you can toggle through going to triple bond and then back to single. You can delete any changes or anything using that eraser there. You can use this wedge tool to create stereochemistry, and then you have your ring structures. And you'll notice that there's no list of atoms. That's one thing that's quite different to other tools. However, to add an atom, you just hover over the bond and you just type in an atom. So Cl for chlorine. So it is quite simple to use. And you can also copy and paste structures from things like ChemDraw. So if you right-click in ChemDraw and click Copy Smiles, you can then right-click in here and say Paste Molecule. Oops. So I'll just delete that one I made. So let's have a look at the scoring profile for this compound. So this does get quite a good score. However, we can see that one property is not optimal for this compound, and that is the hERG inhibition. So that's a key property that we'd like to optimize. So within this Design tab, I can click on this hERG PIC50 property there, and it will switch on the glowing molecule. I'll just resize that to get a better look at that histogram. Right, so one thing that I can see is that the linker region is causing an increase in the hERG inhibition, so that's contributing towards an increase in this property. So I could change that region. I'll create I'll put an oxygen on that region, and that creates a blue region. So one way that you can, there's two ways that you can change the properties. So one way is to decrease the amount of red regions, and another is to increase the amount of blue. So that's created a nice blue region, and you can see that the hERG PIC50 has decreased. We can have a look at this in this table and see what it was before. So that was around 6, and now it's about 5.4. However, if we look at the overall score, we can see that that's gone down quite a lot. And this seems to be due to let's have the brown and orange colors, which is the blood-brain barrier penetration. And as these drugs need to get into the CNS, that is a very important property. We definitely don't want to decrease their blood-brain barrier penetration. Right, so I'll just delete that change. That wasn't a very good one to make. So let's have a look at this left-hand side of the compound. So I'm going to make a different change. I'll just delete this ring structure, and I'm going to put on a 5-membered ring instead. And I'll just create a pyrrole here, and you can see that I've created a blue region. And the hERG inhibition has gone down. And let's have a look at the overall score has actually gone up by quite a lot. That is a good change to make. So I've identified a good compound, and now I'd like to add that compound to my data. So I can click on this Go button, and that will add that compound to my data set. And I can see that, well, it doesn't have the 5-HT1A experimental pKi value. It does have a predicted value, and that's a prediction of 7.5. Right, so that's the end of the third section now. So are there any questions on that section or on StarDrop in general?
Bailey, one thing that I find quite useful is to be able to create a new data set from a selection of compounds, particularly when you're working with big data sets. Would you like to just demonstrate that?
Yes, so that is very useful. So say I identified a few compounds that were very promising, and so I could select these compounds and hold down the control key to select multiple compounds. And then I can go use this tool, create from selection. It's the third one up on the right toolbar. And clicking on that just takes all of those selected compounds and creates a new data set. So there are those compounds. And now I've got 2 tabs along the bottom of 2 data sets. So it works quite similarly to Excel in terms of these tabs.
That's lovely, thanks. Anybody else got any questions? No?
Right, I'll hand over to Ed to give a final wrap up of the session.
Thanks, Bailey.
So yes, if you could just, I think if I stop sharing.
You stop sharing.
Okay, that should allow him to share now.
Okay, yes, so I think I'm sharing again my screen.
Hasn't come up yet.
Okay, let me...
Yeah, it's just coming. There you go.
Okay,
got it.
Brilliant. Okay, excellent. Yeah, as Bailey said, I mean, I'm aware we're a long way ahead of schedule. Nobody normally complains about that, but please do feel free to pepper us with questions afterwards if you'd like to. What I wanted to do, though, was just wrap up with just a little bit more information, just a reminder of some of the things that we've told you, and just sort of a quick reminder of some of those other optional modules that StarDrop does have available. So throughout this session, everything that we've looked at in these examples is based upon the core of StarDrop, but also the ADME QSAR module. So these are the two parts of StarDrop to which everyone in the consortium has access, and everything we've looked at today simply uses those two parts of StarDrop. But of course, different members of the consortium also have access to other optional modules, and I just wanted to briefly remind you of what those modules are, for a couple of reasons. Firstly, if you've got those modules and are interested in some training, then obviously, as Caroline mentioned, we'll be happy to set up some sessions to focus on these particular parts of StarDrop. Alternatively, if you don't have access to them but would like to try them, let us know, and we're happy to arrange a sort of a trial period so that you can try them out alongside the rest of StarDrop that you're already using. So just as a reminder of what they are, you can see I've got the slide up which shows the 9 different optional modules available with StarDrop. I won't go back over the ADME QSAR module because we've been using that today. But all of the different models that we were using today, the logP, the hERG affinity, affinities for different P50 enzymes and so on, were built using a variety of descriptors and modeling techniques which are encapsulated within our AutoModeler module. So StarDrop's AutoModeler module enables you to open a dataset in StarDrop, feed it into the AutoModeler, and from that build and validate robust models which are tailored to your chemistry and to your properties. They use all the different modeling techniques that we ourselves use. They've got our set of descriptors to which you can add your own. As Bailey mentioned, they will produce glowing molecule output from the models that you build. And if you are if you do have a sort of computational chemistry background, you can tailor the way that those work, so pick and choose the methods. We've wrapped it up in such a way that it's accessible to everyone, so if you're not so familiar with model building, you can hit the go button and it will do sensible and robust things for choosing how to split up data sets and build models and give feedback on how good they are. But obviously, if you know what you're doing, you can control that a lot more. So the AutoModeler is a module really for when you've got your own data and would like to build models of your own properties. The P450 module is also a set of models, but this is a set of models which are quantum mechanical. So rather than giving you very quick predictions for any one particular compound, they take a minute or two to make a prediction for each compound, and they then identify for you different sites of metabolism that you might expect to see if your compound is a substrate for one of the major P50 enzymes. So these models give you an indication also of which of those are the most likely to be responsible for any first-pass metabolism that you are seeing. So it is another set of predictions, but the models work quite differently to the QSAR models we've been looking at. Final set of models to mention comes from one of the modules, which is something we've developed in collaboration with one of our a partner organization. So the Derek Nexus models, I'm sure many of you are familiar with the company LASA Limited, who developed the Derek Nexus platform, amongst others. And so the Derek Nexus module in StarDrop provides access to predictions of those knowledge-based predictions of toxicity endpoints. So they're available, again, like our ADME QSAR models, something you can choose from in the models area and add to your data set an indication of the likelihood of there being some kind of toxicity against these variety of endpoints. But of course, it doesn't provide access to the whole Derek Nexus knowledge base. So it's what you might think of as Derek Nexus Lite, but it fits very nicely within the StarDrop framework for giving you predictions that you can factor into your multi-parameter optimization. Moving away from modeling a little bit, but really building on the glowing molecule theme, the NOVA module, rather than StarDrop simply giving you feedback about which parts of a molecule might be interesting for you to modify and explore further, the NOVA module will actually make suggestions of new molecules to you. It can do this in a variety of ways. So we have the ability to do, at the simplest end, library enumeration. But we can also do idea generation, where you identify a scaffold or regions of the molecule you're happy for StarDrop to modify, and it will go away and make changes at those regions and present you back those results. And if you wish, tailoring that based upon you telling it about particular properties or scores of interest to you, so that it tries to improve those properties for you. We can also do matched series analysis within there. So the core of StarDrop that you are looking at today already has a matched pairs capability within it that you can look at within CardView, but matched series analysis goes quite a long way further than matched pairs in terms of the statistical rigor, in terms of the suggestions that it can give you about changes you might like to consider to improve the potency of your compounds. So all of these approaches are wrapped up within the NOVA module, and as a complementary module alongside this, again coming from one of our collaborators, we also have the Bioster module, which works alongside the NOVA idea generation engine to give you access to the Bioster database in order to use that to make changes to molecules as NOVA is exploring different chemistries. And of course, this gives access to sort of 29, it's actually over 30,000 sort of precedented transformations with links back to the literature. So if you find a compound of interest, you can see where other people have applied the same change to their compounds. Down on the bottom row here, the Torch 3D module, I believe some of you already have access to today. So the Torch 3D module comes from our collaboration with Crescit Biomolecular in order to identify, sort of consider the 3D SAR, really comparing your compounds with known bioactives in terms of their electrostatics. So you can consider the likelihood that compounds you're designing are going to be able to interact with the target in a consistent way, given that they're electrostatic patterns. The CSAR module, again, comes from one of our another collaborator. This is Biosolve IT, but this is for visualizing sort of protein ligand interactions in 3D. So it provides a 3D viewer into which you can load proteins, and it happens to work sort of particularly sort of well if you use StarDrop's post-generation interface. So StarDrop itself does not provide any docking or post-generation capabilities, but we have a generic post-generation interface which can and has been connected to most of the well-known sort of docking and post-generation or conformer generation tools that are out there. So this is a way of working within StarDrop, generating 3D conformations externally, bringing them directly into StarDrop. The CSAR viewer provides a way that you can look at those within the context of your StarDrop analyses. And the last module to mention is StarDrop's MPO Explorer. So this really takes the concept of the probabilistic scoring one step further. Quite a common question we get asked is, well, I can create scoring profiles, but how do I know what the right profile to use might be? And of course, what the right profile is quite a complex question. But of course, if you have historical data that you've applied, that you've generated in previous projects, you can use MPO Explorer to figure out which the combinations of properties would have been most valuable in steering you towards the best compounds. So really, it's an automated way of taking many properties and figuring out which are the ones on which it's most valuable to focus, and which ranges of those properties seem to be the ones which are steering you towards the best compounds. Really, it's a way of sort of developing those multi-parameter optimization strategies and also analyzing them, so you can sort of apply it retrospectively to a scoring profile and say, well, how sensitive are the criteria that I've chosen, or how sensitive are the decisions I might make to the criteria I've chosen? And it will give you an analysis of what might happen if you were to tweak some of the criteria in your profile a little bit in terms of the way your compounds would ultimately be ranked. So obviously, I've sort of just touched very briefly on these modules. If any of them are of interest to you, if you'd like to know more, if you'd like to try them out, as I said, do feel free to get in touch with us, and we'll be happy to help you out. But really, the last thing I wanted to finish up with was just a reminder of where there's more information. You've been sort of very quiet in terms of questions today, and I hope that's because it all seems very easy. Obviously, StarDrop is far more interesting when you start to apply it to your own compounds and your own data. So as you start to do this, please don't forget that there is a help menu providing direct access to a user guide and a reference guide. But please don't feel you need to read your way through those before you come to us. We've got this email address at the bottom, and you're very welcome to sort of hit us with any questions that you've got. As I mentioned, the website's got a variety of information that should be helpful, along with case studies and FAQs. We have the online community there, which itself has additional tutorials, walkthrough videos if you don't want to try them out, except the exercises for yourself. You just want to take a look at, I apologize, you'll probably hear my voice in some of those, but hopefully it'll give you a sort of a quick introduction to those, along with some very short hints and tips videos, publications, and so on. But so there's a wealth of information out there, but please come to us if you'd like, if you have any questions, we'll be happy to help. Otherwise, I think I should finish simply by saying thank you very much for taking the time to sort of take a look at this training today. I hope it was helpful for you, and we'd love to hear your feedback.
Thanks, Ed. That's great. I should point out that amongst the script add-ons to StarDrop, there are things like links to Science Cloud and CDD, which I know that a lot of people use for depositing their data on. And there are also nice things like Payne's filters, e-molecules scripts, so you can look up and see if you can buy compounds that you've proposed straight off from a catalogue. So I thoroughly recommend that you have a look at that. And do get in touch if you come up with any kind of problems. We'd love to hear from you. Okay, so if there are no questions, I can't see any in the chat, then I will draw the meeting to a close. Thank you very much for attending. Thanks very much to Ed and also to Bailey, who's done this twice today. Thanks, Bailey. And enjoy the rest of your day. Thanks, guys.
You too.
Thank you.
Thank you very much for your time, everyone.
No problem.